All right, so today is Friday, the 30th. It's one of my kids' birthdays today. Um, we're going to cover 3.6. If you notice, we missed 3.5 and there's no notes for it in this packet. It's because 3.5's goal is to be able to mix everything from this whole unit together. So I want to cover 3.6 and I'm going to mix that in with it as well. So on Monday, we'll be doing a 3.5 3.6 sort of activity that covers everything. So normally we do it as a group activity, but I don't know, I'll see how it's going to work. But we're going to work with higher order derivatives. Really what that just means is derivatives of derivatives. So if I say take the fifth derivative of, let's do the easiest one in the world, e to the x. You'd say the first derivative is e to the x, and the derivative of that is e to the x, and the derivative of that is the e, and you just keep taking the derivative. Don't write this in your notes yet, but if y was, say, equal to 4x cubed minus 2x, the first derivative would be 12x squared minus 2. The second derivative would be 24x. The third derivative would be 24, and the fourth derivative would be 0. So if you can take a first derivative, you can take a higher order derivative. Sometimes they just get a little bit more messy, so the notes are quite short. We're going to focus a lot on the notation, and we're going to start to apply this to particle motion, which will be a whole unit for us in and of itself, or a big portion of a unit later. But just to touch the tip of the iceberg of our particle motion, and what I mean by particle motion is things moving left or right or up and down. All right, so suppose this is a time axis. And this is the position, which a lot of times we call S of t. In physics, they call it x of t, but it's where something is. It's distance at any given time. So let's suppose this was in, let's say, seconds, and this was in feet. And suppose that a ball was thrown straight up from the ground level, and we were recording its distance. And let's suppose its distance, it started at a height of 0 feet. Then after 1 second, it was at a height of, let's say, 10 feet. And then after 2 seconds, it was at a height of, keep in mind, I'm throwing it straight up and it's coming down. I'm not graphing the path of the ball. I'm graphing where the y-axis represents the ball's height. So although you might think it's like a football being launched, it's not. It's something that got tossed up into the air and it came straight back down, and I am charting its height. And I said at 1 second it's 10 feet, and at 2 seconds, let's suppose it's up at 15 feet, and at 3 seconds it's here, and maybe then it started to fall back down. So then its distance from the ground would start to come back. And this would be when it hit the ground, okay? But this isn't the path of the ball, it's the height at any given time. Now take a look at units. Like I said, this was in seconds, and this is in feet. So when we talk about a derivative or a slope of a tangent line, it would be the change in the position, change in y, over the change in time, or change in x, which with labels would be feet per minute. Notice I said feet per minute. That's a speed or a velocity. So when we take the derivative of position, we're actually finding the velocity. So the derivative of position is velocity. We can write that a couple ways. We can say the derivative of position over time is actually equal to the velocity at any given time. Sometimes we call it the instantaneous velocity or the tangential speed. It kind of just depends. Notice right here, where the velocity is 0 is when the ball hit its high, look at me drawing over here, the ball hit its highest point right here, and then it started to fall back down. But in order to do that, it had to stop for an instant to change directions. So notice this is when the derivative or the slope equals 0. And that would be where the change in position over change in time is 0. Which would be then when the velocity is 0, which would represent when that ball hit its very highest peak, stopped, and then fell back down. So when we talk about derivatives, we are eventually going to start applying them, and one of them is with this motion idea. So one thing to know is that if I ever ask you the velocity, you will take the derivative of your position function, okay? And then if I were to take the derivative of that, which we'd call a second derivative, so we would call it the second derivative of position, which would be the derivative of the velocity. And what we get when I do the derivative of the velocity would be feet per minute. Velocities change per minute, and I get acceleration. So I know that was sort of a lot of notation, but really you just need to know this, that when you know the position function, you take the derivative once to get the velocity. Those are usually labeled in miles per hour, feet per second. It's a rate of change, an instantaneous rate of change. And then if I took what we call the second derivative, we'd get miles per hour, feet per second. That's also known as the acceleration of something that's moving. So here's our notation. We're already familiar with all of these. We know we can call the first derivative y prime. We can call it f prime of x, or we can call it dy dx. Well, similarly, the second derivative we call y double prime. We call it f double prime of x. And then this notation sometimes looks weird to people, but it's the derivative of, so watch me write it over here. It's the derivative of the first derivative. I have an extra y in there. I'm gonna go grab my eraser here. It's the derivative with respect to x of the first derivative. So you'll notice you do see notationally these two d's, and then it's dx dx. So that does sort of make sense why that squaring with the y, or not squaring, it's actually, it's kind of a, we'll call it squaring, but the third derivative is y triple prime, or f triple prime of x, or we could say it's the derivative of the second derivative. And you'll notice I do get that d3y over dx cubed. And that can go on forever, so usually we don't take it past the fourth derivative. After that, we stop putting the primes, and if you see what's f21 of x, it wants you to derive that sucker 21 times. Now, the only thing that would be valid for, like, who would want you to do a derivative of something 25 times? That would be silly. So the only time you'd ever be asked that, if the derivative was, say, e to the x or 5e to the x, its 21st derivative would still be 5e to the x. Or maybe you're asked for the 20th derivative of 3 cosine x. Well, what I would do is I'd put my Saint Cloud, negative Saint, negative Cloud. It ends the way it begins. I would hop in at cosine, and I'd go like this: first derivative, second derivative, third derivative, fourth derivative, fifth derivative, sixth derivative, seventh derivative, eighth derivative. And I just go till I got to 20 because it cycles so nice, right? And the constant just comes out front for derivatives. So wherever I landed after doing that 20 times, that won't take me too long. But other than that, the most you'll be asked is probably a third derivative. So let's just practice a little bit because it's pretty easy. Like I said, if you can do a first derivative. So to find the second derivative, or what we call f double prime of x, now you might say, what does it represent? Well, that's coming. We totally know the first derivative is the slope of the tangent line, the instantaneous rate of change. The second derivative is going to have meaning as well. In terms of our motion, it's acceleration, but also just in terms of the nature of the function, it actually is going to represent curvature. It's coming in another chapter though, so you just need to know how to take one. This chapter is just called Derivative Rules. Advanced derivative rules. So let's go take a look at our first derivative would be 6x squared. The derivative of cosine is negative sine, and I have a negative in front of that, so I'd have a plus sine x. The derivative of the natural log of x is 1 over x. The derivative of e to the x is e to the x. And again, if that had been e to the 4x, the derivative of e to the u is e to the u du. So you need to know how to use all your rules. Have them all lined up in your brain. But this said to find the second derivative, which will be the derivative of the first derivative. So it'd be 12x The derivative of sine is cosine. The derivative of x to the negative first, which is what 1 over x is negative 1, x to the negative 2, or equivalently minus 1 over x squared, and the derivative of e to the x is e to the x. There is our second derivative, and those are called higher order derivatives. So you just calculated a higher order derivative. Not so bad. Like I said, if you can take one derivative, you can take a bunch of them. So let's go on here. It says, let's visit a scenario from our first week of class. I didn't do our first week of class this year. I just jumped in right with limits, and I didn't. The first week generally has like some pre-calc stuff and some basic physics stuff. But due to me being worried about time this year, I didn't do that. It doesn't matter. It does matter. It'd be nice if I could have, but it shouldn't affect this higher order derivative stuff. So it says, suppose a ball is dropped from the top story of the Burj Khalifa in Dubai. 2,717 feet above the ground, we're dropping that sucker. The position equation that depicts the height in feet the ball is thrown from the ground at time t in seconds is modeled by, and it's right here. Now this is calculator active, so you can go ahead and use your calculator on it. So what I'd like you to do is go hop on your calculator. I'm going to just hop on my key here, if you don't mind. So when you use, it says velocity. Velocity is the derivative of position. It's how your position is changing over time. So all we do is take our position function right here, and we do the derivative with respect to time now. So I'm doing the derivative of, I'm really doing d dt, because time is my independent variable, of 16t squared. So t is the new x. So it would be a negative 32t minus 10. That's the first derivative, okay? So first derivative, negative 32t minus 10. And it said to find s prime of 5. So I do negative 32 times 5 minus 10, and I get negative 170, and this would be in feet per second. Next up, it says to find the acceleration. Well, the acceleration is the derivative of velocity, or the second derivative of position. So if my velocity function's right here, the acceleration function would be its derivative with respect to time, which is just negative 32. But that would be how the velocity, which was in feet per second, is changing over time. So it'd be feet per second, or feet per second squared. When will the ball hit the ground? Well, it hits the ground, right, when its position is 0. So we're going to have to go take a look at when the position is 0. And this can be solved using your calculator. So what you would have to do is go graph that on your calculator, the s of t, and you're just going to do a calc 0 at where it hits the ground. And so that would end up being, you can go do it on your own, 12.722 or 12.733 seconds. It's a question about at what time, so we're looking for a t when it hits the ground. So that would be when the position function, which was the original function, is 0. And that would require a calculator because it doesn't factor. What will the velocity of the ball be on impact with the ground? Well, we would take the 12.72, the time it takes to hit the ground, the span in time until it hits the ground, and we plug it into our velocity model. So you just do V of 12.722. And that would end up being about negative 417.12. It's a velocity, so it's in feet per second. So just a real rudimentary beginning to what we're going to be calling particle motion, all right? So next one up is about the moon. Because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. That's interesting. The position function for each of these following objects is given by. So this is the position of the hammer and the position of the feather. Okay, where S of t is height in meters and t is time in seconds. If I graphed my model, t comma S of t, right, it'd be an upside down parabola because of the negative in front there. It's a quadratic function. All right, so it says, what is the ratio of the Earth's gravitational force to the moon's gravitational force? Well, you might say, what's gravitational force? It's what pulls an object towards the Earth, and it's how that object is accelerating. So if you haven't learned that in physics, a gravitational force is its acceleration towards the Earth, okay? And so you have a gravitational force right now, and that's what's keeping you from floating. There's a force that's pushing you towards the ground. So right now, if you're standing up, you're accelerating toward the Earth, and that's what keeps you staying put and why you're not floating around, all right? So the question is, or like a car on a hill, even if you don't have any gas, as long as you don't have the brake on, it's going to accelerate down the hill due to the force of gravity. So think acceleration when you think gravitational force, but we won't have many. This might be the only question of the year on gravitational force, but I like it just here at our very beginning. So let's talk about the Earth, because it says ratio. So I'm going to figure out how much stronger the gravitational pull is on the Earth than it is on the moon. So here we have our Earth. We'll do our moon, and then we'll do our ratio of the Earth to the moon. So when I'm done, I'm going to set up a fraction of Earth gravitational pull, moon gravitational pull. All right, so for the Earth, position, negative 0.81 t squared. Sorry, I had to take care of something. I don't know if I paused that right or not, but all right, so, whoopsie. Oh, that stupid eraser. Sorry, the moon's one is the one over here anyway. So we've got the moon's position, negative 0.81 t squared plus 2. Well, that comes from, actually, this is very interesting where that comes from. You won't have it, any questions on this on your first test, just so you know. I'm not going to do that yet, but I'm just sort of introducing it a little bit of the head of time. On the Earth, it'd be negative 4.9. Maybe you recognize that from physics. I don't know how much science background you guys have, but negative 4.9 t squared plus 2 would be what we're on the Earth. So it means it's had an initial velocity of 0, was being thrown from a height of 2 meters. That's all just physics stuff. If that doesn't make sense where those come from, that's okay right now. But the point is to know that I need to go figure out acceleration for gravitational force. So this would be negative 9.8 t, and my acceleration would become negative 9.8 meters per second. Okay, now on the, or per second. On the next one, when I bring this out front for on the moon, I'll take my first derivative, I get negative 1.62 t. Again, I'm just power ruling it with respect to t. And my second derivative, which will be the acceleration on the moon, I get negative 1.67. So the question was the ratio of the Earth's to the moon. So for my ratio, I'd grab the Earth's acceleration due to gravity divided by the moon's, and that would be about 6.049. So the Earth's gravity is about 6 times that of the moon's. And that's kind of an application of a higher order derivative. So do you have to understand all this right now? Not really. I guess what I'd love for you to take out of that until we further our studies on motion is that velocity is the first derivative of position and acceleration is the second derivative of position or the first derivative of velocity. All right, so this is challenging. I wouldn't say that it's challenging. It's just, I guess, keep your signs in order. Your SIGNS is not your cosine signs. All right. So this means find the second derivative. So first thing we're going to do is take the first derivative. The derivative of secant is secant tangent. We had to memorize that last chapter. The derivative of cosecant is cosecant cotangent, but the cofunctions go negative with their derivatives. And that held true for us with our inverse trig cofunctions as well. Remember, those were negative u prime on the top. So there is my first derivative. That didn't seem very challenging, but when I take the second derivative, I'm going to really need to watch those signs, okay? So let's go do it. I'll use the product rule. First, d second. The derivative of tangent is secant squared from last chapter. The derivative of cotangent is cosecant squared, but the cofunctions are negative. So that's first d second plus second. I hate the t's, but we're going to start having lots of t's because time will be our independent variable throughout all of our applications. So t is sort of the new and more popular and more useful x. Where was I? I did first d second plus second, and now I need the derivative of the first function. The derivative of cosecant is negative cosecant cotangent, but I already have a negative in front of it, so it'd be a cosecant t cotangent t. So I guess I don't know that that was all that complicated. When I clean it up, I have a cosecant cubed t plus a cotangent squared t times a cosecant t. And again, you know we should always factor. So we'll take that cosecant t, we'll pull it out front. We'll have a cosecant squared t plus a what do we have? Tangent squared t. All right, I think that's all we need for that one. What else was I going to do? One more example, and the back side of your paper should be blank. I'm going to put it right here. I want you to go back to that circle that we did. X squared plus y squared is equal to 25. When I first introduced implicit, I started with this circle, and I solved it for y. And then I took the derivative explicitly using the chain rule, and then I told you how to take the derivative implicitly. So what I'm going to do right now is go back and do that again. I'm going to find the slope of any tangent line on the circle with centered at 0 with a radius of 5. So again, with our implicit, which you guys were actually really good at, it's 2x times dx dx plus 2y times dy dx. The derivative of any constant is 0 because it doesn't change over time. Okay, so our derivative, our y prime, is equal to negative 2x over 2y, or equivalently negative x over y. That's my first derivative. Now what we're going to do, and remember what that does, it tells me the slope of the tangent line anywhere on the curve. And now what I want you to do is we're going to find this. And this is notation for this second derivative, as is this, as is this. So I try to get you to have some notational fluency here. So I need to take the derivative of my first derivative. But that requires the quotient rule. So I'll go low d high dx dx, and there's a negative. Low d high minus high d low, the derivative of y is y prime. Draw a line and square below. Next, I want it implicitly in terms of x and y. So what I'm going to do is take this y prime and put its xy model in for it. So I'll have the negative y minus x times a negative x over y, because that's what y prime is. So it's just substitution kind of from algebra 2. I know that y prime is this, so I'm going to put it in for y prime. And then I draw a line and I square below. So I end up with a negative y plus x squared over y all over y squared, but we don't leave complex fractions. So when I clean this sucker up, I'll do a little crisscross applesauce or getting a common denominator or whatever you like, but I'm going to have a negative y squared on the criss plus x squared on the cross all over y, and it collapses as a product. So it'd all be over y cubed. This expression will give you the second derivative on the circle, which you don't quite know what it's going to give you practically yet, but that's coming. You'll learn. Just like you know that a first derivative is a slope of a secant line, tangent line, an instantaneous rate of change, you'll know that a second derivative gives you information as well. Right now, we just need to calculate it. So this process is called calculating an implicit second derivative. And the kicker of it is that plugging the y prime value in right there. All right, so your assignment is worksheet 3.6 skill build. I was trying to stop calling them worksheets. I'm calling them skill builders because that sounds better, right? So that's your assignment. Due by when I enter them on Monday morning. All right, so have a good one and see you later.